All right, so part five is going to be all about weak acids and bases. We're really going to be focused though on acids today. So we already know that strong acids ionize completely. So when you take any one of our 7 strong acids and put it in water, essentially 100% of those acid ions turn into hydronium and the conjugate base. So that is a one-way arrow. But we also have lots and lots of weak acids out there, and they actually will reach equilibrium when they ionize. So hydrofluoric acid is a good example. You can see there the two-way arrow tells us that hydrofluoric acid is not going to ionize completely. And in fact, it's not going to probably be even close to completely ionized. So when we start talking about the KEQ expression for this reaction, if it's not even close to fully ionized, in fact, there's going to be a lot more unionized HF than there will be hydronium and fluoride. So the KEQ for a weak acid ionization, which is also referred to as Ka, is always going to be small, which is another way of saying that reactants are favored. So if you look at a table of Ka values, and again, Ka is just KEQ, but it refers specifically to weak acid ionization reactions. So you see these values are really, really small, right? They're all like 1.7 times 10 to the negative 5. We even have like a 10 to the minus 10, 10 to the minus 13. They're all pretty small. So very few of our original acid ions like HF are going to turn into hydronium and fluoride. So here's an example from your notes. Calculate the concentration of hydronium of 0.45 molar hydrofluoric acid. And so there's the little snippet from your table, which gives you the Ka of hydrofluoric acid as 6.8 times 10 to the negative 4. All right, to understand this, the first thing we have to do is write our ionization equation. So you should be pretty familiar with that. We've been doing that for a little bit now. It is a two-way arrow, though, and that tells me that it's a weak acid. So if we set up our Ka expression, our little fraction, so let's think about what's going to go on top and what's going to go on the bottom. On top, we have hydronium concentration times fluoride concentration, and they're always just going to be 1 and 1, so we don't have to worry about any exponents. On the bottom, though, we do have one reactant we have to list, and that is the initial acid, which is HF. The water, of course, does not get included because its physical state is liquid. All right, and in this case, all of that is going to end up equaling 6.8 times 10 to the negative 4. So the question is, how do I find hydronium concentration? So what we're going to do is, just to make it make sense, we're going to use an ice box or ice table. So starting with our initial concentration of HF, in this problem, it's given to us as 0.45 molar. So I'll fill that in. Water is a liquid, so we don't worry about its concentration. It doesn't have one. And of course, hydronium and fluoride are both products, so their initial concentrations will be 0 and 0. Now, hydrofluoric acid being a reactant is going to go down by some unknown amount. The hydronium and the fluoride are both going to go up by that same amount because, again, we have a 1-to-1 ratio. And the good thing is with acid ionization equations, it's all going to be 1-to-1. So that really simplifies things. We don't have to worry about having a coefficient in front of hydronium or fluoride like we may have with a KSP situation. Okay, so we put them together, and our acid ends up being 0.45 minus X at equilibrium. And of course, 0 plus X is just X for both of our products. Now, if I go back to my original Ka expression, it looked like this, right? And if I replace what needs to be replaced, so hydronium and fluoride are both just equal to X, right, at equilibrium. So I'm going to replace that with X squared. And my HF, well, it's 0.45 minus X. Luckily for these problems, subtracting X is not going to be significant. It's not going to be a big enough number to matter. which is going to make it a whole lot easier for me to solve for x because I don't have to worry about quadratics or anything else. I can just say subtracting whatever small number x ends up being from the relatively large number 0.45 is not going to matter. So now it just becomes a matter of solving the equation. So if I multiply both sides by 0.45, that takes care of the 0.45. And of course, take the square root of both sides to get rid of the square. And we get x equals 0.017 molar hydronium. Now that we have hydronium, the next question is, what is the pH? And that should be very straightforward, very easy. We know that pH is the negative log of hydronium, right? So it's just going to be the negative log of 0.017, which is what we just found. That was our x value. So that should end up being about 1.77. And then the last question is, what is the degree of ionization? So that's a new term. It basically just means how many of my original 0.45 moles per liter of HF actually goes through ionization by the time we reach equilibrium. So that formula is simply going to be a fraction. We're going to say, all right, what is our concentration of hydronium at equilibrium? That goes on top, compared to what was the initial concentration of the acid before we started. And so HA just means, generic acid. In this case, it would be hydrofluoric acid, but we're just going to say HA because this works for any weak acid. And since it's a percentage, we're going to multiply by 100. All right, so what are we going to plug in this case? Well, our hydronium at equilibrium is just x, right? So that goes on top, 0.017. And our initial acid concentration was 0.45. And so I'm going to divide those two and then multiply by 100. And we see that only about 3.8% of my original HF molecules ionize and form hydronium and fluoride. All right, last question. This time we're looking for the Ka, and we're given initial acid concentration and pH. So we think about what the ionization equation would look like. And again, this is just a generic weak acid, HA, all right? By the way, I know it's weak because we wouldn't be finding the Ka, right, for a strong acid because it doesn't reach equilibrium, right? So if Ka is involved, we know we're talking about a reversible reaction and a weak acid. So here's my expression. So nothing new here. It's just like the last problem, only we're replacing F minus with A minus and HF on the bottom with HA. Now we don't really have to do an icebox for this one because we pretty much already know that if we did an icebox, what we would find is that X would be my equilibrium concentration of hydronium and A minus, and they would be the same as one another, so it would just be X squared on top. And my initial acid concentration this time is a lot smaller, 0.0085, and that we would say minus X for it on the bottom. Now, subtracting X usually doesn't matter, but in terms of the math, it's really not going to be too hard to just subtract whatever value X has. So we don't have to worry about quadratics or any of that. We'll leave it there for now. We may not end up bothering with subtracting X. So the thing we have to understand is, just like the last problem, X is equal to concentration of hydronium, right? And so there's a way to find X using pH because we know that hydronium concentration is equal to 10 to the negative pH, and we were given the pH of 4.08 in this problem. So if I take 10 to the negative 4.08, I get a value of 8.3 times 10 to the negative 5 for my molarity of hydronium. And then, since I already set up and I already know that Ka is equal to X squared over 0.0085 minus X, I can just plug in what I know now. So 8.3 times 10 to the negative 5 squared goes on top because we still want to square X. And 0.0085 minus X goes on the bottom. Now again, it doesn't really take me a whole lot of extra time to subtract x now that we know what x is, but I'm not going to bother because x is 8.3 times 10 to the negative 5. So I could have put that down there and went ahead and subtracted it, but you're subtracting a number that is 100 times smaller than your original number. So it's not, especially once we round for sig figs, gonna matter. So I'm even though it would be easy to do, I'm not going to worry about subtracting x in the denominator there. And so now I just get to plug in my numbers and find a Ka, which turns out to be 8.1 times 10 to the minus 7 for this unknown generic weak acid.